Welcome back. Let's resume trigonometry. Section 4 is about an application of these two fundamental identities. The addition theorem for sine and that for cosine. They're often called the sum identities for sine and cosine respectively. And by substituting beta by negative beta right here, you're going to get a difference identity for sine and the difference identity for cosine, as we see over here. Pretty simple. Alpha minus beta is the same as alpha plus of negative beta, and then that's how we can prove it. As a matter of fact, well, here we go. Just replace beta by negative beta and simplify, we get what we want. Putting both of those together, we can express a sum and difference identity like this using plus and minus notation. In any case, this is a fundamental identity, the sum identity for sine and the sum identity for cosine. We'll prove it in section 5. Here in section 4, we discuss the applications of these two. First application, the sum identity for tangent. How do we prove that? Well, just remember that tangent is sine over cosine. So tangent of alpha plus beta is sine of alpha plus beta over cosine of alpha plus beta. So sine of alpha plus beta is like this numerator using the sum identity for cosine. And the cosine of alpha plus beta, we get that from this sum identity for cosine. And then what do we do? Divide everything by cosine of alpha times cosine of beta. Because we do the same thing to both numerator and denominator, I do not change anything. And consequently, we have this kind of simplification. From the first term, what do we get? Sine of alpha divided by cosine of alpha, we get tangent of alpha. And cosine of beta just cancel each other out, resulting in this term. From the second term, what do we get? Cosine of alpha and cosine of alpha cancel each other out. Sine of beta divided by cosine of beta, we get tangent of beta. Oops. This one. What about this term? Cosine of alpha, cosine of beta divided by cosine of alpha times another cosine of beta, we get just 1. And finally, from here, sine of alpha divided by cosine of alpha, that's tangent. Sine of beta divided by cosine of beta, we get tangent again, resulting in this term. That's how we can prove the sum identity of tangent using these two. The final step, if you replace beta by negative beta, then you're going to get this expression. So if you put together both alpha and beta, both plus and minus, using plus minus notation, you get this kind of identity. How about the double angle identities? Well, very, very simple. Just plug in alpha and beta equals to theta into this sum identity of sine over here, and this is a computation I'm going to get. Sine of 2 theta is 2 sine of theta times cosine of theta. Do the same thing to cosine identity over here. Alpha and beta are both equal to theta, then we get this kind of computation. Now from here, you can simplify this further using this Pythagorean identity, because sine squared is equivalent to 1 minus cosine squared. So if you do that, you get this kind of simplification. You get 2 cosine squared minus 1. Or vice versa. From here, you can put in cosine squared is 1 minus sine squared through this Pythagorean identity. You get this form. So we have 3 equivalent forms of double angle formula for cosine. Now from here, if I solve for sine squared, and we get this power reduction identity. From here, if I solve for cosine squared, then you're going to get this power reduction identity. From these two, if I replace theta by half of theta, you're going to get this half angle identity and that half angle identity, respectively. Here's several more. Sum to product. Well, here is a rough explanation. Spend some time to go through with these if you want. Just a little bit of tedious computation, that's it. And product to sum. Again, here's a rough explanation. Triple angle identities can be a little bit more complicated because you have to use the standard sum identity and the double angle identity and Pythagorean identity in this and that places and simplify. Same for cosine. And how to use those? Well, you should already know, so I'm going to skip those. All those were justification why we are spending our time on this addition theorem. The sum identities for sine and cosine respectively. If we prove this, then we are done with the proof of all trigonometric identities actually, because everything we did in section 4 was based upon these two, and everything we did in section 3 we already did. Okay, let's prove it. And this is going to be a little bit more complicated than anything else here. Okay, there can be some other ways to prove this, but the method I prefer is to use this digression. I want to establish a rotation in plane first, and then use that to prove the addition theorem. Now, is that really the most effective way? That is arguable because it's a kind of digression, but this digression is very, very valuable because rotation itself is an important topic. Let's talk about it. Here's a visualization. We begin with small x comma y and take a rotation by the angle theta about the origin, and we end up with capital X comma y. And what are the relations between capital XY and small xy and the angle theta? Here it is. Capital X is x cosine of theta minus y sine of theta, and capital Y is x sine of theta plus y cosine of theta. Now, if you prefer the matrix expression, then you may prefer this kind of thing. Capital X times capital Y, capital X, capital Y, excuse me, is equal to this matrix, cosine of theta, negative sine of theta, sine of theta, cosine of theta, times the matrix x, y. This expression that I just highlighted and this expression over here are equivalent. This is just matrix expression, and here we have coordinate by coordinate, component by component expression. They're the same. Now let's justify this and let's prove it. And here is the proof. Pay attention to this picture here, but this picture is not really perfect because we just have the rotation motion of a point. We want to expand this picture a little bit by considering a triangle. I'm talking about this kind of triangle. We begin with this triangle here in the left hand side picture and take a rotation by the angle theta and end up with this triangle in the right hand side. Please note that this red point, small x comma y, is going to be moved over to this point, which is capital X comma y. Consequently, we have all this rotation. My aim is to express this capital X and capital Y using small x and small y and the angle theta. And I claim we're going to get this in the end. Let's check. Here we have this standard picture, and let's find out the capital X. Turns out we have these kind of picture. Let's see. Let's look at the second picture, this right hand side picture, in a little bit more detail. Let's take this blue shading, and X is now hypotenuse this time. Here in this picture, second picture, X is now tilted hypotenuse, and horizontal distance is consequently x cosine of theta, as we see over here. So from the origin, if I move x cosine of theta, then I got all the way over here, and actually I overshot it. Capital X is over here, which means I have to be around here where my mouse is, but I overshot a little bit. So I have to come back left a little bit. How much? Well, that's going to be answered by the second picture here from the red triangle, red shaded triangle. Angle is theta, the top angle is theta, and hypotenuse is y. So we have y sine of theta. That much we have to go to the left. Consequently, what do we have? We have this. X cosine of theta minus y sine of theta. Starting from the origin, x cosine of theta, get over here, and then come back by y sine of theta, which is visualized over here by y sine of theta. These two are just a little bit more detailed picture of the second picture over here, with a little bit more shading and some labeling. First we have this triangle, and this is before picture, and we have after picture, after rotation, and let's scrutinize this after picture a little bit further, and we end up with this blue and that red, consequently generating x equals to x cosine of theta minus y sine of theta, capital X I mean. Okay, let's go over to capital Y. Again, we have to scrutinize this after picture a little bit further, but remember, this time we have to move vertically, we have to go up. And the first step is this. Look at this blue triangle, and I moved vertically by x sine of theta. I still have to go a bit further up because y is all the way over here, so I have to go all the way over here, around here where my mouse is. But I got only from 0 to about x sine of theta. A bit more. How much more? That's going to be answered by this red triangle over here. It is y sine of theta because hypotenuse is y, the top angle is theta, so y cosine of theta, excuse me. So x sine of theta, that's blue, and then y cosine of theta, and that's how we end up with capital Y, as we see over here. Consequence. Capital X is x cosine of theta, and capital Y is y cosine of theta. That's precisely what we wanted to prove all along. That takes care of the rotation in a plane. Okay, a big step. Now let's prove the addition theorem. First, look at this green picture. Cosine of alpha plus beta, comma sine of alpha plus beta will be the position of this green point after alpha plus beta rotation. X, capital X, comma capital Y from this green picture. I did the color coding here as well. Capital X is cosine of alpha plus beta, capital Y is sine of alpha plus beta because they're coming from this alpha plus beta rotation all the way. Now let's look at the first picture. It is equivalent to alpha rotation getting up to small x comma small y, and then beta rotation. Now how about the alpha rotation? Well, that's easy. Cosine of alpha comma sine of alpha, so those are x and y respectively. Now here comes the key part. From x comma y, I have to take a beta rotation to get capital X comma capital Y. That is exactly the same as this one, except that theta is now beta. So that's what we get. Capital X is x cosine of beta minus y sine of beta. Capital Y is x sine of beta plus y cosine of beta. And what is x and what is y? Here they are. Plugging those in, we get this purple expression. Those are about capital X and capital Y. And this green expression is also about capital X and capital Y. Comparing these two, green and purple, we get precisely what we wanted. Cosine of alpha plus beta is cosine of alpha cosine of beta minus sine of alpha sine of beta. Sine of alpha plus beta is cosine of alpha sine of beta plus sine of alpha cosine of beta. if you simply switch the orders, if you switch the order of this one and that one, that's basically it. That's how we prove the sum identity, the addition theorem of trigonometric functions.